Hello everyone, welcome to my class and my channel. So today is a very special lecture on abstract algebra, groups. It's a very important topic in abstract algebra. It's the foundation of abstract algebra. So before we start with the groups, let me give you some definition related to group or some concepts related to groups. First of all, I will talk about binary composition. So what is a binary composition? So you have a non-empty set G. A binary composition on G is a mapping A from G cross G to G. You see, F is a mapping. A binary composition is a mapping from Cartesian product. G cross G is a Cartesian product of G to G. So a binary composition or binary operation. So it gives you from a order pair, it gives you a single element. The mapping is called binary composition or binary operation. Therefore, a binary composition F assigns to each order pair of elements of G a definite element of G. Okay, so you have an order pair A comma B to C, a order pair to a single element. That gives you a binary composition. This mapping is generally denoted by the symbol circle. And the last point is that the symbol like star, plus, dot are also used to denote a binary composition. So you can use different symbols as a binary composition. Also, there are many in textbooks also you will find out. Now, suppose plus is a binary operation on Z. 2 comma 3 belongs to Z. So 2 plus 3 is 5. 5 belongs to Z. So this gives you a binary operation on Z. Subtraction is a binary operation on Z. Multiplication similarly is a binary operation on Z. But subtraction is not a binary operation on natural number because 2 belongs to the natural number, 3 belongs to the natural number. But you see 2 minus 3 doesn't belongs to the natural number. Okay, so subtraction is not a, in this case we say subtraction is not closed under the binary composition minus under subtraction is not closed actually. So n is not closed under my subtraction minus, that is the term we use. But you see addition, so Z is closed under addition, Z is closed under subtraction, Z is closed under multiplication. So this is the term we have to use. Now let us explain the closure property. A binary composition circle is said to be defined on a non-empty set G if A circle B belongs to G for all A comma B in G. So AB belongs to G implies, if it implies A circle B belongs to G, then the binary composition is said to be closed. Then the set G is said to be closed under the binary composition circle. Circle is said to be commutative if A circle B is equal to B circle A for all A comma B belongs to G. So circle is said to be commutative if A circle B is equal to B circle A, or you can use the star symbol also. And for all the elements, not for few elements, for all the elements, that is very, very important. And circle is said to be associative if you see the last line A circle B circle C equal to A circle B circle C. So this is called the associative property. As you have seen in the set theory also, this type of property is commutative associative for all ABC belongs to G in this case also. So in this case we talked about closure property, that is binary composition is closed, commutative property and associative property. Now G is a non-empty set and circle is a binary composition. Then G comma circle is said to be a algebraic structure. Is a algebraic structure, or it can be said as groupoid. So there are common algebraic structures are groups, rings and fields. These are the three main algebraic structures. So we'll talk about groups in this lecture. Actually, if you see, I just mentioned one thing, groupoid. Let G be a non-empty set on which A binary composition circle is defined. Some algebraic structure is imposed on G by the composition circle, and G circle becomes an algebraic system or algebraic structure. This algebraic system is called groupoid. So the common algebraic structures are groups, rings, fields, but specially we'll talk about groups. Okay. So let's come to the definition of group. A group G comma star, or you can say circle, is a set G, and a binary operation on G is a non-empty set such that G is closed under star. And first property G1, for all ABC belongs to G, circle is associative. That is first property, circle is associative. G2, there is E belongs to G called the identity. This is called the identity element such that for all X belongs to G, E star X equal to X star E equal to X. This is called the identity G2. You look at that G2. G2, this is called the identity. Okay, sorry. Yeah. And G3, the last one, for all A belongs to G, there is an inverse element, A prime is called the inverse element of G, such that A star A prime equal to A prime star A equal to E. So these three are the main important properties of groups. To be a G is said to be a group if these properties hold. So G1 star should be associative. G2, there exists an element identity E belongs to G, and that is called the identity element such that E star X equal to X star E equal to X. Number 3, for all A belongs to G, there is an inverse element A star is A prime belongs to G such that A star A prime equal to A prime star A equal to E. So these are the three, and this is from the definition of Rayleigh. You can follow the book. Now, let's have an example, some examples. The familiar groups examples are integers. Z comma plus is a group, set of integers with respect to additions, set of rationals with respect to addition, set of real numbers with respect to additions, set of complex numbers with respect to additions. All are groups. That means they follow associative property. Obviously, they are following closure property. So we don't need to define say the closure property in a separate form, because if you are talking about a binary operation, it should be closed. So integers with respect to addition, it follows must follows associative property. Identity, 0 is the additive identity integers. Okay, because if you take any elements and you as sum with 0, it will give you that element only. So 0 is the identity element, and suppose 2 is an element of the set Z. So minus 2 is the inverse element, additive inverse. This is called additive inverse. 2 minus 2 is 0. So this is how you can define the groups, and you can illustrate the groups with the properties. Rational numbers Q comma plus is a group. Real numbers R comma plus is a group. Complex numbers with respect to addition is a group. And this is integers. Last one is a integers modulo n. That is modulo group. Modulo group. We'll explain modulo group later on. Suppose if you divide the some integers, then you have a residue, right? Residue. This residue forms a group. That is called the integers modulo n. We'll explain this later on separately. So these are the explanations. Also some few examples. Non-zero rational with respect to multiplication. Non-zero rationals, these are also group. Non-zero rational, not zero. Non-zero rational with respect to multiplication. Non-zero real numbers with respect to multiplication. Non-zero complex number with respect to multiplication. It's also groups because they follows the associative property. There must be an identity. Yes, for multiplication, you have a 1 as the identity. 1 is the multiplicative identity. 0 is the additive identity. Okay. Integers with respect to multiplication is not a group because 2 do not have inverse in the Z half. But in rational number it must have inverse. 2 has an inverse half in rational numbers. So that is why set of integers with respect to multiplication is not a group. Okay, so that is why identity is 1, inverse of x is 1 by x in all the cases. Okay. uh, Okay, next we'll define abelian group. You look at that in the last line, you have an abelian group. So if the binary operation is commutative, that is called an abelian group. Extra, that means G1, G2, G3, this is G4. Associative, identity, existence of inverse, and this is abelian. Abelian means commutative. If the commutative property holds, then the group is called abelian group. And for an example, a non-abelian group is that an n cross n invertible matrices under matrix multiplication. You know that matrix multiplication is non-commutative, not commutative in general. So this is a non-abelian group. This is an example of a non-abelian group. All non-singular matrices, all true n cross n non-singular matrices forms are non-abelian group with respect to multiplication. So this is the commutative abelian property already I mentioned. So q comma q plus q star r star c star under multiplication are abelian groups. Uh, More example, the set z plus under addition is not a group since there is no identity element for plus in z plus. The set of all non-negative integers under addition is not a group since there is no inverse for 2. The set z, q, r and c under addition are abelian groups. Okay. Now there are some elementary properties of groups. If G is a group, first theorem, you can say these are the theorems or important properties. If G is a group, then with binary operation star, then left and right cancellation laws holds on G. So that is A star B equal to A star C implies B equal to C. You look at that, A is cancelled. You look at that, A is cancelled. So this is called left cancellation. And B star equal to C star A, this implies B equal to C. For all of BC belongs to, in this case, you see right cancellation holds. So this is called, for all of BC, this is called cancellation properties holds in G, right? Suppose A star B equal to A star C. So we have a proof. You can see the proof. So there exists an inverse A prime to A. So you take the inverse on left, right? You look at that, A star, A prime star, A star B, A prime star, A star C. And you know that in a group associative properties hold. So from the associative law, you can write open bracket A prime star A open bracket star B. So similarly on the right hand side also, and you know that from the inverse property, this is nothing but your identity E. So E star B equal to E star C, and that follows that B equal to C. Similarly, you can do the thing for the right cancellation. So this is the proof, very easy proof for you. You can try the right cancellation also. You have to take the inverse on the right side. Next theorem, in a group G with binary operation star, there is only one element E in G such that E star X is equal to X star E is equal to X. So this is the only one identity. Only you have only one identity. This is also very simple. You can try this. First you have to, I will give you hint for that. You have to assume there is two identity, U1 and E2, and follow the cancellation laws and all that. You can easily prove that the group has only one identity element. And also inverse in each element are unique in a group. Inverse in each element is unique in a group. That is also very easy to prove. You can take it as an assignment and prove that identity is a group has only one identity element, and inverse of an element is unique in a group. Next, it is a very important theorem. In a group G comma circle, A star B inverse is B star. A circle B inverse is B inverse circle A inverse for all ABC. AB belongs to G. So if AB belongs to G, you know that A inverse, B inverse, A composition B, B inverse composition A inverse all belongs to G. The first line, because G is a group, inverse exists, closure property holds, and B inverse belongs to G, A inverse belongs to G, their composition also belongs to G. So these are all belongs to G. Now you have to start with B inverse circle A inverse circle A inverse circle B. So you apply the associative property and follow the that A inverse circle A is identity, and lastly you have B inverse circle B equal to identity. So that similarly you can prove A circle B, you can take A composition B on the left and B inverse circle A inverse on the right. So you can prove similarly this is also E. So that means B inverse circle A inverse is the inverse of A circle B. So hence the theorem follows. So this is very important theorem using the inverse techniques. Now, also there are some important theorem. If G is a group with binary operation star, and if A and B are any two elements of G, then the linear equations A star x equal to B and Y star equal to B have unique solutions x and y in G. Unique solutions x and y in G. This is also you can follow from inverse and associative technique. So first of all, we show the existence of at least one solution by just computing that A prime star B is a solution of A star x equal to B. So you just replace x by A prime star B and apply the associative law, and using the result that A star A prime is nothing but your E star B is B, using the property of E identity. So it follows that x equal to A prime star B is a solution of this equation. In a similar fashion, you can prove that y equal to B star A prime is a solution of this. Right? So this is very simple. To show uniqueness of y, we assume that we have two solutions. This solution is unique, you have to prove also. First of all, you prove that this is a solution. Now you have to prove these are unique. So uniqueness, so y1, y2. So y1 star A equal to B and y2 star A equal to B. Then y1 star A equal to y2 star A, right? And from cancellation laws, right cancellation law, we have y1 equal to y2. So the uniqueness of x also follows similarly. Okay. So this is the very important theorem. So these are the very important theorems and properties. Now, lastly, we'll talk about some finite groups. Finite groups when there exists finite number of elements. So one element group is E comma star. Actually, a group contains only one element. So this is one element group. Two element group, you can say E comma A, and this is by defined by the composition table. And you can define the composition table. On the left, you have left top corner, you have star the composition, and E A, and do the composition. E star E equal to E star A equal to A star E equal to A, and A star A equal to suppose X, and you can easily show that this element can occur exactly once in each row, because this is a composition table. There is a composition table property. Each element in the occur exactly once in each row and each column. So we must have X equal to E. So that is the cross check. You can do the cross check. So this is the two element group. Next, we'll say three element group EAB. So you have X, Y, W, and you can easily prove that X equal to B, Y equal to E, Z equal to E, W equal to A. So this is by the property that every element can occur exactly once in each group and each column. So this is also composition table. From the composition table, you can prove that this is a three element group with respect to composition circle. Okay, so there are some famous books. So this is my first class on groups, so I will recommend some books for all of you. You can follow number 3, number 4. Galleon is a very good book. Number 3, 4. And if you want to see the books for easy language, number 6, SK Mappa, Higher Algebra, Abstract and Linear. And the 7th one is a very important book. You can keep this book up to post-graduation level also. Malik, Moderson and Sen. So this is a very McGraw-Hill. This is a very old book. If you have in the library, just borrow it. It's a very, so these are my references. So that's all for today's lecture. This is the first lecture on groups. Next class will be on some problems. We'll analyze some problems. I will give you some assignment also on that problems. So follow my channel and subscribe my channel. Thank you all of you.